Okay, hi everyone. So I'm going to talk about Mesh2faust, which is a tool that comes part of the Faust distribution that allows you to go from 3D meshes directly to Faust physical models. So my name is Romain Michon, and I'm a researcher at INRIA and at GRAME, and also lecturer at Stanford University. So the first thing I want to talk about very briefly is physical modeling in Faust, because Faust has some history with physical modeling, as I'm sure you probably understood at this point, and you probably know about it. And I just kind of want you to get an overview of the different things that you have in Faust to do physical modeling. So the first one is just the Faust libraries in general, because the Faust libraries, the Faust signal processing libraries, implement hundreds of functions for real-time audio DSP. So basically this is your first main resource that you can use to implement physical models in Faust. In fact, the workshop that I'm teaching this afternoon, we're going to look at that into more details to implement a car engine physical model in Faust. And for that, we're mostly going to use tools that are coming from the Faust libraries and not necessarily other things. So for those of you who never programmed in Faust, that workshop is a good way for you to sort of get started in Faust and to actually do some physical modeling from scratch using Faust. Okay, another tool is the Faust SDK. So I think that was kind of the first step towards physical modeling in Faust. And the Faust SDK is a re-implementation of the SDK, which is the synthesis toolkit that initially was created by Perry Cook and Gary Skevan in the United States. And about 10 years ago, we did a re-implementation of all the SDK physical models in Faust, and that actually gave birth to the Faust SDK. So this is kind of a historical overview of what has been done, once again, for physical modeling. So later, what we did was to create the Faust Physical Modeling Library. So the Faust Physical Modeling Library allows you to implement physical models using waveguide and model techniques. And basically, all the models that were part of the Faust SDK were completely re-implemented using the Faust Physical Modeling library. And so for now, if you want to start doing physical modeling in Faust, it's probably the easiest way to do it. You know? And by the way, all these slides are available online. I'll give you the URL at the end, and you can click on the different links that are actually part of the slides, you know, like if you actually want to explore this. Later, another tool was created, which is called MIMS. This tool was a collaboration that we had with some people in Grenoble, with James Leinert and Jérôme Villeneuve. And MIMS is a tool that allows you to create mass interaction physical models using Faust and a graphical user interface. So for those of you who are not familiar with physical modeling in general, mass interaction physical modeling basically works by connecting masses with virtual springs to create vibrating structures and objects. And so with MIMS, what you can do is basically just connect these masses and springs to create physical models. And then all the rendering is done in Faust, because what the user interface does is that it creates a Faust code, basically, that you can then compile and use with any Faust target that you might want to use. Okay, another thing that you can use for Faust for physical modeling is finite difference scheme in Faust. And this is actually the fruit of the work from one of Stefania's students at Aalborg University when he did an internship with us a year ago. And his name is Ricardo Russo, and he implemented a set of tools to do finite difference scheme physical modeling in Faust, which is, I would say, a little bit more advanced than all the other techniques that I just mentioned before. So this is actually very interesting work, and for those of you who are not familiar with it, I really recommend you to actually have a look at it, because it's kind of a very novel approach to implementing finite difference scheme models just in general, not just in Faust. And finally, I just want to mention that in the industry, people use Faust for physical modeling. And I think the two most famous examples of that is Expressivy and Mesh2faust. Expressivy is a French company based in Paris, and they make hardware and software for music technology, and they develop audio plugins, and some of the plugins that they develop use physical modeling implemented in Faust. And then there is Mesh2faust. Mesh2faust is an American startup based in Silicon Valley, and they make iPhone apps using physical models which are implemented in Faust. So once again, those are interesting links. I just advise you to sort of have a look at them at the end of the presentation. So today I'm here to talk about Mesh2faust. So once again, Mesh2faust comes for free as part of the Faust distribution. So if you want to use Mesh2faust, you just need to download Faust on your computer, install Faust, and then install Mesh2faust. So Mesh2faust is a command line tool, and basically what it does is that it takes a volumetric mesh and converts it into a Faust model, physical model, by extracting model information from the result of a finite element analysis. Okay, so what does that mean? It means that basically you can make a 3D object in Blender, in OpenSCAD, in SolidWorks, in Rhino, whatever you want, okay? And then basically you can give it to Mesh2faust, and then Mesh2faust will turn it into something that you can hear, and into something that you can use in Faust. It basically makes a playable physical model in real time from your 3D object. It is based on the Vega FEM library, which is developed at Stanford, and the Intel Math Kernel library. So for those of you who are not familiar with the Intel Math Kernel library, all you have to know is that it can be really tricky to install, and it's also very, very, very big. So all that to say that if you want to use Mesh2faust, you need to have some free gigabytes on your hard drive, because you're going to have to install all this stuff in order for it to work. And this is done automatically. You just have to look at the documentation of Mesh2faust. A wide range of parameters can be configured to specify the material properties of the model, the behavior of the generated model. So it means that if you want to use a specific kind of material, say copper, wood, brass, or whatever, you can configure that directly in Mesh2faust, and then there are many, many parameters that you can control to refine the physical model you're going to get from it. Okay, finally, generated models are compatible with the Faust physical modeling library and can be combined with other elements, other parts that are actually part of the Faust physical modeling library. So in the Faust physical modeling library, you have, say, for example, strings and bows and bridges of string instruments, and you can actually connect that to the generated model of Mesh2faust. Okay, I'm not really going to go into too many details about this because I don't think I have too much time for it, but this is kind of an overview of how Mesh2faust actually works. So it takes a volumetric mesh as an input, a .obj file, and .obj file is basically just like an STL file for those of you who know about STL files. Okay. Then you can specify material properties and some parameters for the model, and then all these things happens. You see that basically what we use is an eigensolver. The eigensolver generates eigenvectors and eigenvalues, which are then turned into mode gains and mode frequencies, and finally into a Faust object that you can use with a Faust physical modeling library. So for those of you who are familiar with this kind of physical modeling, one thing that you might notice here is that we are not using a damping matrix, which means that Mesh2faust will not allow you to compute the duration of resonance of all the modes of the object. So that's something you have to specify by hand. And the reason why we're not doing it is because it's a little bit more complicated than just doing all the stuff that we have here. So basically, this was kind of a first step. And adding damping matrix is something that should be done probably in the future. Okay. So because at GRAME like open source, we wanted to provide people with a completely open source framework to work with this. And So there is actually an alternative to this, which is by using Blender, because Blender is completely open source. And one of Stefania's students a couple of years ago implemented this thing called Blender2faust, which basically is based on Mesh2faust and allows you to just draw something in Blender and then export it to a Faust physical model using Mesh2faust. Okay, so another alternative is to use Inkscape and then convert your Inkscape 2D drawing to OpenSCAD. And there is a tool in the Faust distribution that actually allows you to do this. Okay, so it's like an Inkscape plugin that exports Inkscape 2D drawings to OpenSCAD. And then you do the 3D in OpenSCAD and then finally use Mesh2faust. Okay. So very quickly, I'd like to give you a very short demo of making a Marimba physical model using all of this. Okay, so sorry, I need to exit the full screen mode. So basically the way you would do this, is first by creating, for example, a Marimba bar model using OpenSCAD. Okay, so once again, OpenSCAD is completely free and open source. So this is a Marimba bar object, okay? Then all you have to do is to export it as an STL file that you could 3D print, okay? Or turn into a physical model. So after this is done, you probably want to open the generated file. Sorry, this is not very practical. In MeshLab, okay? And then in MeshLab, but that's okay, I think you can. So the reason why you want to use MeshLab for this is because usually when you use CAD softwares, the mesh that is generated by CAD softwares is completely optimized, which is very bad for what we want to do because we want a mesh which is completely uniform, which means that basically, I'm sorry, I think there is a problem with the screen, but basically you want something that looks like this where you have as many triangles here as possible and they need to be sort of spread across the model. Well, if you export a mesh directly from OpenSCAD, it's going to be optimized. So for example, like the flat surface you have here on the Marimba bar is going to be completely optimized by using just maybe 2 or 3 triangles. If you want to turn this into a physical model, it has to be completely even, completely spread, okay? And this is something that you can do in MeshLab. There is a tutorial, and I'll give you the link to the tutorial that explains you how you can de-optimize the mesh to get to a mesh that is going to look like this, okay? So once this is done, what you do is you can you can write a script, for example, and you just go in the command line, and in command line you call Mesh2faust, okay? Then you give it your Marimba bar object that I just told you about. Then you can specify all sorts of parameters, and you can specify excitation positions that you might want to use. Like say that, okay, I might want to strike it here, I might want to strike it here, or here, or here on the Marimba bar. And finally, you provide material properties, okay? And those are material properties that you can find on the web very easily. In this case, I think it's just wood, so you have material density, Young modulus, and that kind of material properties. And finally, you give a name to your physical model. If you run this command line in your terminal, in the end, what you get is a Faust library file that is going to look like this, okay? And so this is basically your Marimba bar physical model, okay? So once you have your Marimba bar physical model, all you can do is potentially open it in the Faust web IDE, okay? And I'm sure you know about the Faust web IDE. Okay, sorry, I think the resolution of the screen is very, very low, okay? And so I already uploaded it here, just for the sake of time. But I could add another file here, and in this file, I could potentially just put the code that I prepared for you in this, oops, sorry, this is not very practical. Okay, so this is my Marimba bar model. Okay, so I'm going to copy this, put it in the Faust web ID. Okay, so what we do here is we basically call the Marimba bar model that was generated using Mesh2faust. Okay, I didn't do it in real time because it takes some time to generate the model. Okay, so for this kind of model, it's probably going to take, I would say, between 10 and 15 minutes to actually get the model. Okay. And finally, what you do is that you can send it an impulse. Okay, so this is a button, and when you press the button, it creates an impulse. The impulse goes to the Marimba bar model, for which we configured some parameters. And finally, we send it to a Marimba bar resonance tube, and that's the length of the tube, 1 meter. Okay, so Marimba bar going to a tube. And finally, you run that into the Faust web IDE, and this is not going through the speakers, so well, it's a low bar, you know, like the frequency of the bar is actually 60 hertz, so we don't hear it very well here, but you can potentially try that directly on your computer, because I can just give you the slides. Okay, I lost the presentation. There we go. So I think I can take questions now. If you want to get access to the slides of this presentation, you can find them here at this address, karma.stanford.edu/talks/PAW21. And if you want to actually get a tutorial on what I said, because that was very quick, I just advise you to follow this link. Thank you very much.